Now you can show this, right? So starting from the fact that if x of t is real, this implies that x of t is equal to its complex conjugate. Okay, so this is the sign for complex conjugate. Okay, so on the left-hand side, we have x of t, which is the summation of ak e to the j k omega naught t, where k from minus infinity to infinity. Okay? And on the right-hand side, we have the complex conjugate, which is ak, okay, complex conjugate e to the minus j k omega naught t. Okay? So this is x of t, right? And because x of t is real, it must be equal to its complex conjugate. So if you take the complex conjugate of this, right, it will be equal to the summation of the complex conjugate of a times the complex conjugate of this exponential, which is e to the minus j k omega naught t. Okay? Now, if you perform a change of variable where you set k prime equal to minus k, then you have summation of k prime from minus infinity to infinity, a minus k prime complex conjugate, e to the j k prime omega naught t. Okay? So if you do a change of variable where you set k prime equal to minus k, right, then this still goes from minus infinity to infinity, but now k becomes minus k, and this minus k here becomes k. Okay? Now, if you compare this term and this term, right, for the same k or k prime term, you can see that ak should be equal to a minus k complex conjugate. Okay? So this implies that ak should be equal to a minus k complex conjugate. Okay? Or you can write this as, let's say, ak complex conjugate equal to a